1 civilization has the power of an entire planet. They control the weather. They mine the oceans. They control volcanoes. They control earthquakes. Buck Rogers, Flash Gordon, would be an example of a Type 1 civilization, a planetary civilization in space. A Type 2 civilization in space controls the output of a star. They play with stars. They are immortal. Nothing known to science can destroy a Type 2 civilization. Ice ages can be modified. Meteors, comets can be deflected. Even the death of their sun is not a problem. They can either move their planet, reignite their star, or simply find a new star in space. This is a Type 2 civilization. A typical example of a Type 2 civilization comes from science fiction. The Federation of Planets, Star Trek, would be based on a typical Type 2 civilization. And then we have Type 3. A Type 3 civilization is galactic. They control the energy output of an entire star. For me, this is very interesting, because a Type 3 civilization would be able to control the Planck energy. The Planck energy is the energy at which space becomes unstable. Space begins to boil at the Planck energy. The Planck energy is a quadrillion times higher than the Large Hadron Collider, and gateways, perhaps, wormholes, doorways, portals, perhaps to other dimensions, begin to open up for a Type 3 civilization. So we have Type 1, which is planetary, Type 2, which is stellar, and Type 3, which is galactic. But one day, I was speaking in London, and a little boy comes up to me, 10 years of age. A little boy comes up to me and he says, "Professor, you're wrong. There's Type 4. So I look down at this little boy, this pest, and I tell him, "Shut up, kid. Why don't you go play in traffic? There's a nice intersection over there." And he kept nagging me, and he says, "Professor, you're wrong. There's Type 4. And I said, "Look, kid, we have planets, stars, and galaxies. That's it. There's nothing else. These are the only platforms for advanced civilizations." And the little boy kept saying, "No, you're wrong. There's Type 4, the power of the continuum." Now, for you Star Trek fans, you know that the power of the continuum is the cube. There is something beyond galactic, and that is dark energy. There is an energy source beyond the galaxy itself, making up 73% of the entire universe, dark energy. And then the question is, if we start to explore outer space and look for advanced civilizations, why don't they talk to us? Why don't they land here in Saudi Arabia and say, "We come in peace"? Well, my attitude is, if you walk down a country road and you see an anthill, do you go down to the ants and say, "I bring you trinkets, I bring you beads, I give you nuclear energy, take me to your leader"? Or maybe you step on a few of them. Maybe we're simply not that interesting. So let me now close on the following note. What lessons can we take from this? First of all, this has theological implications. Giordano Bruno was burned alive 400 years ago in 1600 for saying that there are civilizations in outer space. Because if so, the Catholic Church said, do they have a pope? How many popes are in outer space? 1,000? 1,000,000? 1 billion popes? How many saints are there in outer space? The mind boggles thinking about billions of saints, billions of popes in outer space. Rather than think about billions of popes, they simply burned Giordano Bruno alive. What does it mean for us? What are we? Are we type 1 that control the power of a planet? Are we type 2 that control the power of a star? Are we type 3 that can control galaxies, alter the fabric of space and time? No. We are type 0. We get our energy from dead plants, oil and coal. But take out a calculator. How long will it take for us to become type 1? The answer is 100 years. Around the year 2100, we will become a type 1 civilization. And we see the beginnings of that now. What is the Internet? The Internet is a type 1 telephone system. We are privileged to be alive to see the birth of a type 1 telephone system. What is the European Union? The European Union is the beginning of a type 1 economy. Why are we here today? We are seeing the birth of a type 1 economy. What is football? Football is the beginning of a type 1 sports. Get on the Internet. What are the most common languages on the Internet? Number 1 is English. Number 2 is Mandarin. We are beginning to see the beginnings of a type 1 language. What is rock and roll? The beginning of a type 1 youth culture. What is Chanel and Gucci? The beginning of a type 1 high fashion. So let me tell you that we are now witnessing the greatest transition in the history of the human race. Transition from type 0 to type 1. The generation now alive is privileged to see the birth pangs of the birth of a new civilization, type 1. Planetary, planetary energy, planetary economy, planetary environment. And so in conclusion now, let me wrap up. I'd like to dedicate my comments to Giordano Bruno, who 400 years ago said there are planets in outer space. Every week, we discover a new planet orbiting another star. I call this Bruno's revenge. Thank you.
After that, it's just going to be out there in deep space for maybe millions or billions of years, who knows. Yeah, maybe discovered by some future alien race, thinking, what the heck, what were these guys doing? Did they worship this car? Why do they have a little car in the car? That'll really confuse them. I'm not sure what's going to happen, but I think, it's kind of a fun thing, and I sure hope that next burn works, by the way.
But I think this is one of the great questions in physics and philosophy, is where are the aliens? Maybe they're among us, I don't know. Some people think I'm an alien. Not true. Not true.
But maybe we are alien.
Of course, I'd say that,
maybe we are alien. Do you think we'll make contact with alien within the next 50 years?
Well, that's a really tough one to say. I mean, if there are super intelligent aliens out there, they're probably already observing us. That would seem quite likely, and we just are not smart enough to realize it. But I can do some back-of-the-envelope calculations, and any advanced alien civilization that was at all interested in populating the galaxy, even without exceeding the speed of light, even if you're only moving at, say, 10 or 20% of the speed of light, you could populate the entire galaxy in, let's say, 10 million years. Maybe 20 million years max. This is nothing, in the grand scheme of things.
So Elon, you are really quite unique, I feel, in being so interested in the long-term future of humanity.
Well, I think I'm that unique. You have an institute. Clearly, you're interested in that too.
Quite the opposite. I'm curious, your interest in the far future of humanity, when did that begin? How did that start?
Well, I think it was when my interest in the future of humanity is, I guess, as a function of reading a lot of sci-fi and philosophy as a kid, and then and just sort of thinking about, okay, what's important to do? Like, why do anything? What's the meaning of life? And I came to the conclusion that what we really need to do is make sure that life continues into the future, and particularly conscious life. And in doing so, we'll be better able to understand the nature of the universe and achieve greater enlightenment.
One thing I really admire about you is you don't just talk about the future of humanity, you actually start companies and do things about it. So what made you so audacious?
Well, I don't really think of these things as all that audacious. They seem like natural things to do. It's sort of more of a long-term optimization rather than a short-term one. I just not that I think everyone should be doing these things, but someone needs to do them. So if I see that, well, somebody's not doing this and maybe I could be helpful, then I try to do something in that regard.
Weren't there some people along the way though who told you that that's crazy to start a space company or a new electric car company or a solar company?
Sure. I mean, there are lots of people that said that the likelihood of failure was extremely high, and that it was a stupid thing to do. And when I started SpaceX, one of my closest friends got a compilation of rocket failures and made me watch the whole thing. And there were lots of people that tried to talk me out of it. And the joke was, how do you make a small fortune in the rocket business? Well, you start with a large one. And I got told that joke so many times that I obviously I knew the punchline, so I just tell them the punchline, and they would look at me like, "Is he serious?" Or it's like, say, "Why did you start a rocket company?" I was trying to figure out the fastest way to turn a large fortune into a small one. That seemed like a good way to go. But the thing is, I already thought the probability of failure was high, and that with that the likelihood of success was therefore low, so this was not new information. I thought maybe SpaceX had, I don't know, 10 or 20% chance of success, and Tesla probably similar. I thought SolarCity had a much higher chance of success, but probably still only, I don't know, 50% or something like that. Yeah, I mean, for the longest time, and SpaceX and Tesla almost didn't survive. I mean, it came very close to perishing as companies. In 2008 and 2009, with the Great Recession, was an extremely close call.
Looking ahead, what do you think are the technologies that are going to have the greatest impact on society?
So I think there's there's probably five categories. There's and I'm not giving a particular order, but making life multiplanetary, achieving sustainable production and consumption of energy. Obviously, the internet as a whole. I mean, the continued growth of the internet. And then potentially, if we do this, reprogramming human genetics, and the fifth one would be artificial intelligence. So, working on the kind of the first three, but not the last two. I think the last two I think have the greatest potential to be a double-edged sword.
So when you call artificial intelligence a double-edged sword, can you talk a bit about the positive edge first? What do you see as the greatest benefits we can get from AI?
Well, the greatest benefits from AI would probably be in eliminating drudgery. So, like in terms of or tasks that are mentally boring, not interesting. There's arguably breakthroughs in areas that are currently beyond human intelligence, or at least for now beyond human intelligence. I think we could probably solve them in the long term, such as the classic sort of curing cancer and addressing diseases of aging, Alzheimer's, and all these things. So there's insert various like intractable problems to human intelligence. Currently, what seem to be intractable problems, and then if you had something that was way smarter, it could solve those problems.
And turning to negative edge, right?
Well, I think it's best to prepare for to try to prevent a negative circumstance from occurring, than to wait for it to occur and then be reactive. So, and this is a case where the range of negative outcomes some of them are quite severe. So it's not clear whether we'd be able to recover from some of these negative outcomes. In fact, some of you can construct scenarios where recovery of human civilization does not occur. And when the risk is that severe, it seems like you should be proactive and not reactive.
I'm really quite curious why you've decided to make such a large donation, because 10 million is something that really enables a massive amount of research.
I don't think 10 million is a large amount of money for this subject area. It should probably be higher. But there should be probably some much larger amount of money applied to AI safety in multiple ways.
Well, I want to thank you again so much for this. It's something we really, really appreciate and are eager to do great stuff with.
And look how close the mission statement of SETI is to the one that NASA chooses for itself for exoplanet exploration. To explore, understand, and explain the origin, nature, and prevalence of life in the universe. Jill, I think we have a lot in common by our mission statements. Maybe there's more we can do to pull in that direction. If you go to the SETI website, which I'm sure many of you have, they add one more item to their mission statement, which is to apply that knowledge gained back here on Earth to guide present and future generations. So go out and bring back. That theme is recurring, and you'll see that in some of the slides I'll show you later as well. All right, so a couple program slides. This is the scope of the Exoplanet Exploration Program, which I have the privilege of managing for JPL for NASA. We have space missions in the upper left, including Kepler K2, the WFIRST mission, which I will describe. We do studies for future missions. Some of you have heard about Starshades, as a way to find exoplanets and look for signs of life. We study those missions in coronagraphs. This is the next generation of exoplanet missions. I'll put these in context for you. We do some ground-based work with Penn State and the University of Arizona and the Keck Observatory. We do a lot of technology development. We invest in the future. Technology enables exploration, and we are the vehicle for that at NASA. We include the NASA Exoplanet Science Institute at Caltech. A lot of the images and the data that I'll be showing you is drawn from a consistent database, three-dimensional database of our local galaxy. And, well, we have an interesting and active communications group. Who have seen these travel posters before, these exoplanet travel posters? Well, that's something we created, and I'll tell you a little bit more about that when we get closer. This being a NASA talk, I've got one or two org charts. I just need to show these. So we are a program within NASA's Science Mission Directorate Astrophysics Division. So those of you who know NASA, this program reports into Paul Hertz and Andrea Rosaghi in the Astrophysics Division. We're one of a set of themed programs. The others are Cosmic Origins, Physics of the Cosmos, managed by Goddard Space Flight Center, and the Explorers program, also at Goddard. You can find your favorite missions on this list. Under Cosmic Origins, you can find Hubble and Spitzer. Under Physics of the Cosmos, you can find Chandra. And under Explorer, you can find TESS. And this is the final org chart. And at JPL, we manage this program for NASA. We've attracted a lot of great talent to this program. It's a very exciting area. People are drawn to it, and we have the privilege of working on these different missions, not just at JPL, but across the country, working with Caltech. We work with the Goddard Space Flight Center. We work with the Ames Research Center on Kepler. We work with the University of Arizona, with Penn State. In this collaboration for the search for habitable worlds and life in the outside the solar system. All right, so enough on the program. Let's talk a little bit about some science updates. So first of all, it's not even been a month since we saw 7 planets above the fold. What an exciting, amazing discovery, this TRAPPIST system. It really ignited the public's imagination so wonderful to find 7 planets, roughly the size of Earth, orbiting a cool M-star, transiting, only 39 light years away from Earth. What a wonderful discovery, really, really terrific. Let's look at how this fits. These are planets that all fit well inside the orbit of Mercury. They're orbiting a cool M-star. There it is in comparison to our solar system, and you can see how tightly packed this system is. Very strange. We weren't expecting to find 7. Even the scientists said, wow, we weren't quite expecting this. This was a discovery by Belgian astronomers and then augmented by the Spitzer scientists using the Spitzer Space Telescope for a 20-day observation. And 3 of these are interpreted as being in the habitable zone. So I think we all understand what the habitable zone is. It's the Goldilocks zone, not too hot like Venus, not too cold like Mars, just right for life, where liquid water could possibly exist on the surface. Anybody who's been camping knows what the habitable zone is. Here's a group of hardy campers. They have found the habitable zone, and they didn't use Koparapu, they didn't use any equations, and we just lost that. Okay, let me just pop that back in. Okay, that's an odd one there. Okay. So even my file has disappeared from the... Let's try it again. So I had it set up. I knew this might happen, so I set it up so it would pop up. Let's try that again. Oh, there it is. Okay, let me just find the right slide, and we'll go right back to the campfire. That must have been a hot campfire. Now, the campfire for TRAPPIST-1 is much dimmer than the campfire for our sun, and that's why the habitable zone can be much closer in. Smaller campfire, bring that circle in. That's where the habitable planets are. And the reason for this is that this star is much smaller than our sun. There's our sun in the lower right. You can see its radius and our terrestrial planets nearby. There's TRAPPIST-1. It's about the size of Jupiter, just slightly larger, and yet its planets are similar to those of our terrestrial planets in our solar system. What an interesting and unusual system. What a wonderful surprise to discover these planets. This is the Spitzer discovery. This is how they were discovered. We see all these great images on the New York Times. Those are artist concepts. This is what the scientists actually observed. They were watching a time series in a photometer on a detector on the Spitzer Space Telescope, and they saw dips in the light curve, slight dimming in the star. This is the method that Kepler used to find the exoplanets so successfully all these years. And so they saw all these dips, and these dips correspond to the different planets that are transiting. The Belgian astronomers thought they'd found 2, maybe 3. That third one turned out to be another several. So they were able to come up with this set of 7 planets as a result of all of these dips. Occasionally you'll see like a little spike. I talked to the Spitzer scientist, Sean Carey. They're actually residual solar flares. So this is not exactly beachfront property here on this M-star. We think these planets are in resonance with each other, and that these planets are likely tidally locked, meaning one side is really hot and the other side is much cooler. So where would you want to hang out for habitability? Right along the terminator. Along terminators, it might be just the right temperature there. So you'll see here in the artist concepts, the artist actually tried to indicate this when they were drawn. So if you look at the planet D, which is sort of looks like the most interesting one, it's kind of roasted on one side and sort of uncooked on the other, a little bit like a marshmallow, just a little too close to that campfire, indicating that E, maybe that's a better place, maybe a little bit more temperate, and F is starting to look a little chilly on the right-hand side, being further away. So this is the artist's attempt to draw some imaginary images from the data that was obtained from this system. So E, F, and G are nominally reported to be in the habitable zone of this star. So let's take a trip using eyes on exoplanets. This is something you can look at on our website. It's a 3-dimensional visualization that's tied into the NextEye exoplanet database. And so we're going to go first to our sun, and the bright stars are those that have exoplanets. This is 3-dimensionally correct with stars in our local galaxy. And we're going to use the tool to go visit TRAPPIST-1, 39 light years away. So we didn't have to travel very far. And so here's the simulation of TRAPPIST-1. Again, all correctly timed in with when we believe the different transits are occurring. And let's go have a look at D. Here's this interesting one here. The artist imagines, oh, there it is, kind of cooked on one side and potentially water or ice on the other. And then looking at this system, imagining where is this habitable zone, it shows it to you so you can see E, F, and G in that habitable zone band, sitting around the TRAPPIST campfire. So this is the Eyes on Exoplanets. This was featured in the news release, and you can use this to visualize any of the exoplanets that have been discovered so far. Yes, sir? How old do they estimate the star system to be? I think it's not as old as our sun. So it's younger than our sun. It's a middle-aged M-dwarf, they call it. Fortuitously, and by design, the Kepler K2 mission observed TRAPPIST for 80 days, and they finished observing at the beginning of March. So there's the Kepler field in the lower left. Back in May, when they were determining where to point this telescope for this particular 80-day period, they tweaked it to include TRAPPIST because they knew something interesting might be happening here based on the early results from the Belgian astronomers. And so Kepler points in different tiles in the ecliptic for 80 days, and they chose this field, and they expect good photometry on TRAPPIST-1, given the transit depths. What the scientists will be looking for is, can they pin down the period of that outer planet H, because they only saw one transit of H, and is there anything else lurking in that solar system? Does it stop at 7, or is there something else out there? the scientists were able to determine not only the size of the planets, but also their mass from the Spitzer data because of the way the planets tug on one another. They transit with slight variations in their timing because they're tugging on each other. And that tugging reveals their mass, and that mass was determined for each of the planets. And so here they are. And so these are the takeaways from the TRAPPIST system. The richest set of Earth-sized exoplanets ever found. Again, the scientists said, wow, including 3 in the habitable zone. Shows that M-dwarf stars, the most common type of star in our galaxy, can host rich planetary systems. And we can expect more discoveries like this in the future. Systems like this will be great targets for follow-up for the James Webb Space Telescope. Planets that transit roughly the size of Earth around cool M-dwarfs. Those are very easy. Those are the easiest targets for James Webb to do spectroscopy on, transit spectroscopy on. It'll be a hard job, but for the ones that are exoplanets that we know about, these are the ones that James Webb will be targeting. And finally, for us to really get for the general case though, we're going to need direct imaging to look at the atmospheres of these planets. James Webb's only going to be able to look at a few of these because transiting stars are not the norm. Transiting planets are not the norm. All right, let's look at some other results, some other science results. These are Kepler's verified planets by size. So there on the y-axis are the number of planets. This is a histogram. And on the x-axis, you can see the different sizes of planets. Across the top, you can see our solar system. Here are the rocky planets, Mercury, Venus, Earth. Here's the ice giants and the gas giants. And if you look at this, one thing pops out. Look where most of the planets are. They're in a size bin for which we have no analog in our solar system. The most common type of planet that Kepler is finding in the galaxy, we have no analog in our solar system. Somewhere between Earth and Neptune, you go from being rocky, great real estate, to Neptune, maybe not so much. So the universe and the galaxy is revealing itself to be abundant and unusual. When you look at what we call the occurrence rates, when you account for, well, let's see, the smaller ones that are harder to find, and accounting for all the statistics of the observation, removing your observation bias, scientists will determine what they call occurrence rates. How common are the different sizes in the galaxy? The large planets turn out to be relatively few. The most common are the Earth, super-Earth, and mini-Neptune. Super-Earth maybe being up to roughly twice the size of Earth. So look at that ratio. It's 15–20%. Wow. In fact, these results are about a year old. There's a group in our community called SAG-13, led by Russ Belikoff. He's in the audience right now. Give us a wave, Russ. I just saw him walk in. Russ, his preliminary results is that frequency may be more than 20%. It may be as high as 60% for Earth-sized planets in the habitable zones of sun-like stars. Wow, 60% of the stars that are sun-like having Earth-like planets in the habitable zone. Gonna have to update the Drake equation. All right, how exciting. So this is all yet to be proven out, but this is the trend, this is the direction the science seems to be going. The galaxy appears to be abundant. And so these are the key takeaways from Kepler. On average, there's at least one planet for every star in the sky. Wow. So when you look up at the sky, imagine every one of those, on average, has at least one planet. And you can see, what, on a dark night, you have to leave San Jose or Pasadena, but you can see 6,000 or so. And there's 100 billion in our galaxy, at least. Second is that small planets are the most common, and that Earth size in the habitable zone are also common. What a wonderful result that we're learning from Kepler. This is just coming into our knowledge and our understanding over the last couple of years. All right, well, let's look at the total number for a little while. So we're going to call this Mamajek's law. Eric Mamajek predicted a few years ago that the exoplanet doubling time for the number of exoplanets was doubling every 27 months. And this is his plot over time of the total number of exoplanets that are confirmed. Jesse Christensen has nicknamed this Mama Jack Law. He is now, was from the University of Rochester. He is now the Deputy Program Chief Scientist. Where are the rocky planets? So we love all planets, great and small. Got your icy, your gassy, we're particularly interested in the rocky because we're on a rocky planet, so we're curious naturally. Where are the rocky planets? So this is another plot that scientists will make. On the y-axis, different axes now, that's the radius. Bigger planets up above, smaller planets below. And on the x-axis is the mass. Little planets on the left, big planets on the right. So there's Earth and Venus, they're two located there. And so you'll see, Earth and Neptune. Look at Neptune. Neptune's out there, it's about 10 Earth masses, and it's less dense. It's less dense. It's got a much larger radius for its mass. Earth is along a line of constant density, somewhere between rock and iron. So astronomers plot this. For the few planets where we can manage both the radius and the mass, we can get the density, and we can locate them on this plot. So for all the thousands that we've measured, there's only a couple hundred on this plot. A trend emerges. A trend emerges. Somewhere between Earth and Neptune, remember, this is where we're finding most of the planets, there's a transition. Somewhere at around 1.6 times the radius of Earth, or 10 Earth masses, you go from being small and rocky to big and gassy. Something happens in planet formation, and scientists will spend a long time arguing over what this is, where in the formation, you grow to a certain point, and either you stop or you keep growing, and you accumulate a lot of gas in the solar system. So when we debate what is an Earth-sized planet that might harbor life, we tend to be looking at planets up to about 1.6 times the radius of Earth. By the time you get to 2 Earth radii, everything seems to be very gassy above that. Somewhere between 1.6 and 2, there's a transition. So this super Earth, this mini Neptune area, is an interesting area we want to keep exploring. Okay, so where are the TRAPPIST planets? This is the results of the paper. So let's locate them on there. Oh, look, right there, right over by the Earth. They're all rocky. What a wonderful discovery, the TRAPPIST system. Another great discovery last August, a discovery of the nearest exoplanet around Proxima b. People ask, well, where's the nearest exoplanet? You can't get any closer unless you begin to imagine exoplanets that don't need a star, and some people do, by the way, called rogue planets. But this is the nearest one orbiting a star. It's orbiting the nearest star. And again, this is another planet in the habitable zone around a small M-dwarf. This is Proxima Centauri compared to the size of our sun on the left. It's part of a triple star system. Alpha Cent A and B are very similar to the size of Earth. And this planet orbits Proxima Cent B in close, again, well inside the orbit of Mercury in a habitable zone around that star. Again, prone to flares, so you want to get towards the night side at least if there's a flare. All right. And then a final science slide. Typically, we search for planets around sun-like stars. They're easy to find around M stars, smaller M stars. But scientists will actually find them around the larger stars from time to time. And here's a way. A planet was found around an A star. Generally, you can't find them because of all the stellar activity. But this planet was identified by the phase modulation of the stellar pulsations. So I would say this just goes to show that the planets are common and that given a chance, scientists will figure out a way to find them, even if they can't find them today. Okay. Oh, and here's an actual movie of a planetary system that's about 140 light years away. This was first detected in 2009, and just last month a couple months ago, they started making this movie. They've been taking this image. These are self-luminous planets. They're large, warm, glowing under the heat of their formation, not prime real estate. These are planets that are sort of well outside the orbit of Jupiter. And yet, this is a vivid illustration of planets orbiting a star not that far from Earth. All right, how do we discover and characterize exoplanets? Let's take a quick look at that. Many of you actually do this work, so I'll do as quickly as I can and introduce it to the others. So the first thing you'd like to do is just get rid of the starlight and expose the planet next to it. That would be the easiest thing to do. It's really hard. It's like finding a firefly next to a searchlight, but the firefly and searchlight are on the East Coast, and you're looking from the West Coast. In fact, it's about 1,000 times harder than that. So we can find ways to do that. I mentioned the coronagraph and the star shade on the first slide. I'll show you how we do that on some later slides. Another way that we would do this is using the astrometric method. This is a way of looking at the planet tugging on the star, and as the planet tugs on the star, you can't see the planet, but the planet, the star moves relative to other fixed stars, revealing the planet that is orbiting. That's the astrometric method. Here's another way. We like to call this the wobble method. Same basic concept, but now the planet is tugging on the star, and the star is moving towards you and away. Towards you, it's the Doppler shift. The light is shifted blue, and away, the light is shifted red. This has been the workhorse of the early discoveries of exoplanets, this Doppler wobble method. We'll talk about that again in a bit. Oh, here's what's really been generating all the exoplanets. This is the transit method. Statistically, some fraction of the solar systems will line up edge on. Less than 1%, but some of them will. And the planets, if they're there, will transit the star. And that they will cause the light from the star to dim by a small fraction of 1%, parts per million, or hundreds of parts per million. And if you build a sensitive enough photometer, you can see this, but you have to stare for a long time. And that's what the Kepler spacecraft did. And that's why it was so successful. You have to stare at a lot of stars, though, so you need a wide field of view. Another method is called microlensing. This is pretty cool. It uses relativity. And what you do is you stare at a background star that's very far away, and then something passes between you and the background star and causes the light to bend, and it amplifies the brightness of the background star. If you watch that brightness over time, you'll see a significant brightness. You can infer that something passed between you and another star. If that object passing between you and the other star is itself a star that you can't see, but it has a planet orbiting it, this little light curve will have a little blip on it, revealing the presence of an exoplanet. Wonderful little technique, and it's being used right now. Here's exoplanets as a function of time. In 1989, a 12 Jupiter mass planet was found, but wasn't considered an exoplanet at that time. In 95, 51 Peg, that's the generally recognized first Jupiter-sized planet around a sun-like star. And then radial velocity, the wobble method, was used to find many. Then the transiting planets started to be discovered. And over time, microlensing, direct imaging, they actually found planets by microlensing. And then in 2009, Kepler was launched. Look at the green bar. That's the transit method. And the transit method has produced this enormous bounty of planets. Just staring at a patch of sky that would hide behind your hand in the summer sky in the constellation of Cygnus. That's where it looked. And here's the total statistics. It's very hard to keep that plot up to date. So I just put this plot in, and it's already probably out of date, but it's only a little bit over a month old. So got a little problem here. Must be those solar flares. So a tremendous number of exoplanets. But we want to learn more about them. And what are things we're interested in learning? We're interested in learning not just their radius and their mass and their orbit. Interesting. We really want to get at what's in the atmosphere, or maybe what's on the surface, which might be somehow revealed by the atmosphere. There's different techniques, but if we want to get to the atmosphere, we're looking at direct imaging. And we need to do a special type of direct imaging if we're to look for those that are not just self-luminous and glowing under the heat of their own molten formation. So let's talk about a little progress towards where NASA set us off 6 years ago, and then we'll look forward. So being from NASA, we are an organization of documents. The documents guide us. It's the Decadal Survey. New Worlds, New Horizons was the document in 2010. And NASA flows us down through science plans and implementation plans. And I work towards Paul Hertz's instructions in this plan. And so what are the items that are called out in these plans? The items that are called out include WFIRST as the large, the next large mission to follow James Webb, but we must finish Kepler. So Kepler is in its closeout. So Kepler is now in its final data processing. This is the last year of the Kepler, traditional Kepler mission. It's delivered almost all of its products, and this spring it will make its final update for those occurrence rates and new planets that may be revealed as they've finished tuning their algorithms to search for rocky planets in the habitable zone of Sun-like stars. And of course, after Kepler is complete, we will have the discoveries, and we also need their documents. It's always the documentation that takes so long, right? And the final occurrence rate products are on track. But Kepler continues to work right now under the model named K2. Now, a few years ago, Kepler lost 2 of its 4 reaction wheels. Reaction wheels are what engineers use to point spacecraft on orbit, and generally you need 3. So anybody that's taken a physics class knows, oh well, you can't point the spacecraft. Not so fast. The Ames and Ball engineers figured out a way to use solar pressure off the roof line. Look, Kepler has a roof line on its solar panel to stabilize that axis. Wow, to make up for the missing pointing. Well, that's never going to work, right? No, they made it work. The trick is they could no longer point to a patch in Cygnus in the summer sky. They needed to point in the ecliptic for patches 80 days at a time. That's what's indicated on the screen. No problem, there's exoplanets there too. And so they've been making many discoveries, including observing TRAPPIST-1. They'll be turning Kepler around for what we call Campaign 16 a little bit later this year. It'll point in the forward-facing direction. They'll be looking for mini supernova in a neighboring in galaxies as part of its supernova science, which is beyond just exoplanets. And they've also been performing microlensing, and those results will be released soon. So some of you can look forward to that. In the program is the Wide Field Infrared Survey Telescope. This is a project that is managed by the Goddard Space Flight Center. JPL provides a coronagraph, which is the instrument for the alien world. So the science is dark energy, infrared survey, and alien worlds. It's a wide field, hundreds of times the field of Hubble. It's what we call in Project Phase A right now. It's heading for a gate in October of 2017. And we're working with Ball Aerospace and Lockheed Martin on concept studies. One of the topics is making it Starshade ready. Those of you who follow Starshade need to have Starshade to work with a telescope, and NASA is asking, should we make WFIRST Starshade ready? I think we should, because of the science that it enables, and I'll talk a little bit about the science that a Starshade can enable to complement the science of a coronagraph on WFIRST. We work with the University of Arizona for the Large Binocular Telescope Interferometer. So one of the things we have to worry about when we're looking for planets is dust. These other systems have dust in them. What does that look like? Well, this is called zodiacal dust because it's in the zodiacal plane. On the left is an image, one of the best I can find on the internet, from the Atacama Desert, showing before sunrise the zodiacal dust. This is dust, cosmic dust in the inner solar system that's reflecting the light of the sun and reaching our eye. The sun hasn't risen yet. This is the dust in our solar system. Well, if we have dust in our solar system, I wonder if we have dust in their solar system. That's the exozodi, and this is a simulation of a planetary system many parsecs away. And if it has dust in that system, it will make it hard to see a dim planet relative to the dust. And so we're looking for systems that are not much dustier than ours, certainly no more than 10 times dustier, otherwise it's going to get in the way of the detection. So how are we doing? Well, they've looked at 15 stars so far. Good news, it's not that dusty for the ones they've looked at. So we do this by looking at a null, and we look at blue calibrator stars and red science stars, and you hope that it's just as sharp for the science star in the red as it is for the blue in the calibrator star, and not like this. If you look at a calibrator star and then you look at a science star, the dust in the other system would blur out the null and reveal the presence of dust. And so for many of the stars they've been looking at, they in fact are finding that they're not dusty, at least at the level of 6, 7, 8 times that of our solar system. It's good news. We're working with Penn State on an advanced radial velocity, an advanced wobble method to take us down to the next level of precision. And they're due to commission on Kitt Peak in 2019. This will be used to follow up on the discoveries from the TESS project and to look ahead for the systems we might look at for WFIRST. And here's an example of the progress they're making. They call this NUID, and it's next to another instrument that they're delivering, HPF. This is what these radial velocity instruments look like. They're basically instruments inside boxes. They need to be very stable. All right, we also manage technology. We have a technology plan where we describe the technology needed to enable these future missions to find rocky planets around sun-like stars and look for signs of life. And we work with the NASA Exoplanet Science Institute. Last summer school is called Is There a Planet in My Data? And this year will be on microlensing. All right, so forward planning in science and technology to be prepared for the next decadal. So here's the arc of exoplanet missions that NASA conducts. Hubble and Spitzer weren't designed as exoplanet missions, but we see the great results, particularly from Spitzer recently on TRAPPIST-1. Kepler-1 is nearing the end of its lifetime. TESS will launch in 2017, James Webb in 2018, WFIRST around 2025, and we're looking forward towards future missions and designing them now that would actually take us not from finding these planets, but to characterizing them and looking for signs of life in their atmospheres. We call those, the New Worlds Telescope, Habitable Exoplanet Imager, and LUVOIR are candidates. What might K2 and Kepler forward to WFIRST to James Webb for follow-up? Of all the planets that are found, we're looking for Earths and super-Earth candidates orbiting cool dwarfs. Those are the ones that Webb can see, James Webb can see. It'll be using the transit method, not the direct imaging. So there's a few there from Kepler. TESS is going to help us find more planets that James Webb can look at. This is an image from Eyes on Exoplanets showing all the exoplanets. The stars with exoplanets are indicated in bright. Those that are relative to the sun have this geometry. There's quite a few around the sun. That big thrust over in that direction, those are the Kepler targets. It stared at one patch in the sky, so it found a whole bunch in that one column. They tend to be hundreds or thousands of light years away. A little bit too far for the James Webb Telescope. And so that's where TESS comes in. So whereas Kepler looked out in one pencil beam, TESS will look around the whole sky, and it will look much closer, about 10 times closer. Brighter stars, more photons, easier to follow up. Look forward to those results. And the WFIRST telescope will use microlensing to finish the survey begun by Kepler. So think of this as a census. Kepler found planets, I think too close to some signal or something. So TESS, Microsoft sells the aliens. So Kepler began a census, but Kepler's census could really only go out to periods roughly that of Earth, because it only looked for 4 years around sun-like stars. And to finish that census requires that we use WFIRST for microlensing. The microlensing from WFIRST is sensitive to the planets that are further out, beyond what we call the ice line, out where Jupiter and Saturn lurk. And it will film those planets in that blue area, and that will fill in the census and help us understand the demographics in our galaxy. And so what will Mama-Jack's Law look like 10 years from now? Well, those are the projections from TESS and WFIRST. I think we're on track for another 10 years of doubling every 27 months. This is another parameter plot that scientists will draw, looking at the contrast ratio versus the inner working angle. You can sort of see our solar system down here in the lower left. Our solar system moved out 10 parsecs, a little over 30 light years. Earth is down in the lower corner. Jupiter is easier to detect. So where we are today, we're able to detect planets that are way up to the right, far from their star and right. WFIRST will take us a long way, next big step with the coronagraph. But what we want to do is get down and find Earths around sun-like stars. And that's our challenge. Now, our challenge to do that is we've got to get rid of the photons from the star. That star is only a point. What you see there is the diffraction. We can't get rid of diffraction, but we can manage it. We can engineer it by blocking out the light. How might we do that? We might block it out by using an internal occulter called a coronagraph. Basically, you put a mask inside the telescope and you steer the light away. Or you can fly an external occulter, a starshade, to block that light out. Let's look at a coronagraph. A coronagraph looks at a star. The light comes into the coronagraph. The light traveled perfectly for hundreds or thousands of years, but got a little distorted as it came into the telescope, and the telescope itself puts in a diffraction pattern. So we put a coronagraph mask in, and we just steer that diffracted light out to the outer annulus, and we put a washer in and block it. And so get rid of that starlight. The planet, since it's slightly off axis, sneaks past all those filters and lands on our detector. But we still can't see it. Why not? Those perturbations on the coronagraph created all kinds of speckles. But we used deformable mirrors to shape and take out the errors in the telescope. And by using an algorithm called wavefront sensing and control, we can slowly but surely reveal exoplanets hiding in this dark hole. That is the basis for the WFIRST coronagraph. This has been demonstrated on the ground, and we'll go to space, and we'll take it to the next level. Let's look at a starshade. Now we're just going to get rid of the light before it enters the telescope. We're going to launch a separate spacecraft. They're going to unfurl from a central hub. That central hub is going to deploy, and it's going to form a starshade with an optical shield. All those petals are shaped in such a way to send the light away from the inner part of the telescope. You fly the telescope in the shadow of the starshade. They're about 35,000 kilometers apart. And, all right, there's a little artistic license here, but it will reveal the presence of exoplanets orbiting their star. That's the concept of the starshade. And here's some examples of starshade deployments that we're conducting at JPL, showing the deployment in the lab with all this is one motor that reels in a cable, and mechanical engineers will see that we're turning parallelograms into rectangles, and that's how we deploy the structure automatically. An open wheel won't do, so we need to package an optical shield to block the light, and so this is the origami method. Turns out Origami Plus, a set of summer students, can really move the technology along. And so we're scaling this up step by step. And then how do starshades and coronagraphs compare? Scientists study both methods, and it turns out that for relatively small apertures, small 6 meters and below, the starshade is favored because the starshade can see closer into the star. It lets more light through. Those are good things for exoplanets. And you can find a greater yield. As soon as you get out to greater aperture sizes, or you want to find more exoplanets, you want to use a coronagraph, because starshade is not just like pointing a telescope. You have to move the starshade, and the starshade gets limited by fuel. And these are missions that NASA is considering for the New Worlds Telescope, LUVOIR, HabEx, Origin Space Telescope. And so these larger missions will help us in our ultimate quest, which is to look for signs of life on these worlds. And so the signs of life that we're looking for will include looking for habitability, blue of the sky, water, and potentially biosignatures, oxygen and methane. A lot of debate in the science community about what is a positive indicator versus a false positive, but these features, as we see in the Earth spectrum, would be strong indicators that there's something interesting there for habitability or signs of life. In the interest of time, I think I'll skip over some of these slides and indicate that NASA is continuing to invest. And one of the things that they picked recently, just yesterday in fact, was to study the Starshade mission for further study flying with WFIRST. It's not part of WFIRST yet, but to study a Starshade mission to enable WFIRST to do that exoplanet detection. A Starshade with WFIRST will allow us to find exo-Earths in the 20s. Imagine that. Exo-Earths in the 20s. And, all right, I took a picture from my whiteboard. We were sketching, but we'd be able to survey 30 or 50 systems. And depending how abundant the planets are in the galaxy, how high Russ Belikov's Eta number is, we may find a handful or more of exo-Earths. And for some of those, if they're bright enough, with integration time, see signs of habitability, water, or maybe even signs of oxygen, which would be an indicator of biological activity. These are the technologies that we're advancing for coronagraphs and for starshades. So, in the interest of time, let me end with you had me at habitable. So there's quite a bit of interest in exoplanets. It's really a great connection with the public. But I think all of us as professionals also feel that. And what's that about? There's just tremendous interest. When we publish the TRAPPIST results, we put out a new Exoplanet Travel Bureau poster, imagining and placing ourselves on that world. And we've really connected strongly with the public on this. And I thought to myself, what is this? Is this curiosity? Is it wonder? And I think it's more than that. And let me address that on 3 slides. And I'll just start with, quickly, a little bit of my story. So, as Jill described, like many of you, I was inspired by Carl Sagan's Cosmos and his poetry in describing the galaxy. I watched it with my dad, who's a World War II vet. He was in the Royal Air Force. And the motto of the Royal Air Force was, per ardua et astra, through struggle to the stars. So my connection with my dad was he did the struggle and I do the stars. It's always good to find some connection with your dad, right? But influence for many of us goes back to our teachers. I had a great teacher in first grade. Myrtle Folsom was her name. And she challenged us to imagine, this is back in 1970, that there might be something beyond Pluto called Planet X out there in the infinity waiting to be discovered. That was a big concept for a 6-year-old. But here's a picture of me and Myrtle just before her 102nd birthday. Yes, I stayed in touch with her and imagined her delight in learning that there were exoplanets beyond Pluto. And so I became interested in the field. I pursued a career at NASA, and I wondered, the first time I saw the Milky Way at the Philmont Scout Ranch. I grew up in Jersey, so you didn't see the Milky Way growing up there, but I did in New Mexico, and I wondered, as Carl Sagan did, on these other worlds, are there beings who wonder as we do? And I jumped at the chance to be part of NASA's exoplanet exploration program to search for habitable worlds and life beyond the solar system. They had me at habitable. I claim that the connection for exoplanets goes even deeper than wonder and curiosity. It will be a long time before humans ever travel to an exoplanet. We don't know how. Maybe they will one day. That hasn't stopped the NASA JPL artists from imagining what these worlds are like. These are the different NASA travel posters. And no one in this room will ever travel to an exoplanet. They're just too far away. Grandparents will not see their grandchildren grow old. It's just not possible. But exoplanets, like children, represent hope. Hope is the word I think that exoplanets bring in. They represent something of the future, something beyond us, something of infinite possibilities, the possibility that we are not alone in the galaxy. Exoplanets, like children, are a promise of the future and something really wonderful for today. And to drive that point home, I'll end with this one slide. This is our team's motto, which is very similar to a SETI motto, by the way, exploring a galaxy of worlds while inspiring our own, bringing it back home. We went to Pasadena Astronomy Day, and we met a family taking a picture in front of our travel posters. This is a family in the LA area that named their child Kepler, after the astronomer, after the mission after exoplanets, because they love exoplanets. His name is Kepler Cloutier. Look at him in that little jumpsuit. Isn't he adorable? Here is Kepler. It's not showing on here, but he's only about 9 months old here, but he's 33 on, I think, Kepler 16b. And on TRAPPIST, he's much older than us. And so here's a picture of young, we invited him to JPL. And here's a picture, some of you will recognize Steve Howell, the former project scientist of Kepler. And he spent the day with us, played with some of our planetary buddies. And so how do you come up with a caption for this? You know, show me the planets, you had me at habitable. Thank you very much for your time.
Oh, thank you so much for that, and for ending with hope and inspiration. I think that was wonderful. Let me start with the first question, and that's, why do we stop at methane and oxygen and biosignatures? Why aren't we interested in the mathematicians as well as the microbes?
I personally am, but NASA's scope only goes that far. So I think where you're going with this is the reason why many of us are involved in this field personally, but it is not part of NASA's charter as charter to the Exoplanet Exploration Program.
I think that the charter could use some revision. Okay, anyone who would like to ask a question? We'll start with you.
Thank you. That was a great talk. So speaking of charter and revision, we all know that NASA's budget is tied to the federal budget proposals of any given administration. So I was wondering, given that this is a long-term plan, what shields you have, or sunshades or whatever, to protect your budget, and how safe is that timeline under the vagaries of changing administrations?
Well, that's a really hard question to answer. But what I will tell you is we lay out these 5-year plans, and we tie ourselves into the decadal survey. And the Congress looks carefully at what the decadal survey recommends. And the decadal survey pulls from the most compelling science across astrophysics and across, and there's different decadal surveys across the Science Mission Directorate. So I think the best defense is a good offense. And our offense, if you will, is to provide the most compelling science for the decadal survey and Congress and the public to choose from. And I've put my career and my time into what I think is the most compelling science, looking for habitable worlds and for signs of life.
What technique is being brought to bear to improve radial velocity measurements down to 0.5 meter per second?
The question relates to the wobble method and what we're doing to get that sensitivity lower. More stable reference oscillators, more stable systems, more time on the telescope, and the experience that comes from design, build, assemble, test. I can give you a more specific answer. I'd need to look that up. But Penn State has been building a series of these, taking advantage of what's been learned by the Europeans on the HARPS instruments and applying that at the next level down. So this is an incremental build. One of the things that's being looked at to go even beyond the 30 centimeters per second that Penn State is looking at is to get above the Earth's atmosphere. You've got the stellar activity and the tellurics of the Earth's atmosphere. We don't have any plans to go above the Earth's atmosphere for radial velocity now, but that is one of the studies that NASA just commissioned last Monday to look at that possibility. And then you've got to deal with the stellar jitter. Bill.
David, thank you so much for a very extensive, comprehensive talk. Well, one of the things you started out talking about, though, was SETI. Is there any opportunity for SETI and NASA to get together to work on, after all, the first discovery of life might well be by SETI? I know for a while Congress set rules against that, but I don't know whether that's changed.
Mm-hmm. So Bill asked, what are the possibilities of SETI and NASA working together? So right now, SETI and NASA do work together in small ways. SETI scientists work on SOFIA. SETI scientists work with the Kepler project. But your question goes to something greater. And it's true that NASA and SETI NASA hasn't funded SETI since the early 90s. So there are people who set policy and they set the funding. But I think what we can see here from the material that we have in front of us today, Bill, the discoveries that your mission have provided for us, and look at the common mission statements that we have between the NASA big questions, the NASA exoplanet exploration program, and the SETI mission statement. They're all very collinear, and I think they speak to a common human yearning to show that we are not alone. And I think if there's a possibility of us joining forces and answering that question, we really should explore it. But I don't know of anything actionable in front of us right now, except to continue that discussion.
Hi.
Hi.
I'm interested in whether or not there's any work being done to detect auroras on these exoplanets, the importance of them being that they would indicate a magnetic field, and if you've got a magnetic field, that would provide you with some shielding from cosmic radiation, which would in turn protect life forming on the surface of the planet.
So that's a great question. I don't know the answer to that. I've been to a number of science conferences. I'm not a scientist myself, but I do know these questions get asked along with finding exomoons and other features of planetary systems. And so that is probably at the level below our detection threshold now, but it hasn't stopped scientists from beginning to ask that question. And as I alluded to earlier in my talk, if there's a science question that's interesting, eventually scientists find a way to answer that. So I'm not aware of anything active in the missions that we have planned, but I know scientists ask that question. And there may be somebody in the audience who can answer that question. Yeah.
University College London as a group is basically working on detection of H3+. University College London as a group working on detection of H3+ emission, which is a type of aurora that you can detect at 3-4 micron. And there is also a group at Observatoire de Paris who is trying to detect the decametric emission from the magnetosphere of systems with planets.
So there's the possibility, if we can imagine a valuable physical natural system that we want to observe, or natural process, that process will reveal itself in some way, and scientists like the gentleman to your right will eventually find the measurement technique that picks up on how it reveals itself. Yes, sir.
Yes, you presented some experimental data on, which planets are rocky and which ones are gas. Are there any, solid theories, that help us understand what the threshold is, what factors impact that?
Well, yes, there are a number of planetary formation models that are active in the community, and they are models of the galaxy which are informed by the data. So there's a back and forth between the data and the models. But there are some models that support the formation of rocky planets under certain processes that support the formation of the larger gaseous planets. And so, yes, there are models that are driving the observations, and there are observations that are driving the models. And so there, again, maybe some experts in the room that can give you more specifics on that.
Okay, Frank, you get the last.
Hi, very good talk, thank you. You mentioned that ultimately the goal is to image exoplanets, to characterize the atmosphere and see the surface. We had various talks here at SETI Institute on how we could build an instrument to image and characterize exoplanet from the ground. People have been presenting that over the past 3 weeks, for instance, using mid-infrared observations or improving GPI, the Gemini Planet Imager, which is also funded by NASA. Is there any interest from NASA to continue this kind of investigation, to fund this kind of investigation instead of investing in expensive space-based telescopes?
Well, sure. So the question is, can you, what is NASA's interest in ground-based observations for answering these questions? So, so NASA, by its charter, and we talked about charter before, not including SETI currently, our charter for NASA is space. So NASA complements the work on the ground. So NASA won't invest in the ground per se, ground telescopes, but we are aware of it, and the studies that we conduct for these large mission studies will be informed by what the National Science Foundation and other private organizations are accomplishing on the ground. So we're aware of the capabilities of the ground today. We're aware of the capabilities that will be out 10 and 20 years, you know, with some uncertainty. And there are areas of parameter space that the ground will excel at in a working angle and detection, particularly in the near IR. But there'll be some targets based on, you know, our conversations with the ground where we'll want to take it to the next step. So an Earth around a sun-like star is going to be, you know, at or beyond the capability of the ground as we understand it today. So NASA will complement the ground, but will not directly fund those ground-based investigations. But we certainly keep track of that. Thank you.
Okay, Carrie, I'd like to present you with our SETI mug, and maybe that will remind you of the benefit for looking for the inhabitants as well as the habitability.
Right, let's do that.
And let's thank our speaker.
But on the other hand, I have to say that about 6 months ago, NASA's chief scientist actually said, we're going to find life within 20 years. So I guess she wants, you know, that cup of coffee too. Now, was I merely being provocative? Was I simply whistling past the graveyard? No. If you ask, when are we going to find anything? Well, for example, finding a needle in a haystack, and this endeavor has been likened to that. If you ask, how long will it take you to find that needle, Bob? Well, it depends on only 3 things. How big is the haystack? How fast are you going through the hay? And how many needles are in there anyway? And for SETI, we know 2 of the 3. We know how big the haystack is. We're looking in our galaxy, mostly in our galaxy. Secondly, we know how quick our experiments are, and they keep getting faster. This is something the public doesn't really understand. Thanks to developments in digital electronics, our ability to sift through the sky looking for signals is doubling roughly every couple of years. It's basically following Moore's law, and that will continue for a while. Now, this is all contingent upon funding, which is a large part of the reason you're sitting here today, right? This is all privately funded, the SETI work. But assuming that the funding can be found, what this means is that in the next 24 years, we will go through 1 million star systems. So that's like looking for that needle in the haystack and replacing a teaspoon with a skip loader, right? If you can go through the hay more quickly, you're going to find something sooner. So it was on that basis that I made this bet that we'll find something within 24 years, or you get a cup of coffee from me. My wife is buying Starbucks stock. All right. I would say that the chances here have probably been enhanced by the results that have been found by people like the Kepler team and so forth that give us some idea of how many habitable planets might be out there. The current wisdom is that maybe 1 in 5 stars has a world that could be a locale for life. Okay, 1 in 5. Now, maybe it's 1 in 2, maybe it's 1 in 20, but all those numbers are the same number. That means there are many, many, there are tens of billions of cousins of Earth out there. Now, at the SETI Institute, you see the Allen Telescope Array there behind me. We're embarking on a program to look at 20,000 red dwarf stars. Now, you may wonder, what is red dwarf? Is that a British TV show? Red dwarf is, in fact, a very small kind of star, and it's the most common kind of star. Just like everywhere else in nature, there are more small things than big things. Okay, 3/4 of all stars are red dwarfs. So if you were to be plopped down into the middle of the savannas of Africa, you can bet that the average distance to the nearest ground squirrel is going to be less than the average distance to the nearest megafauna, you know, I don't know, an elephant and a lion, something like that. So if we look at 20,000 red dwarfs, instead of 20,000 stars like the sun, on average, they're going to be a factor of 2 closer, and that means a factor of 4 stronger signals. They're also they're dim bulbs. They're like my brothers, okay? These stars burn forever. Every red dwarf that's ever been born is still out there in its teenage years burning today. That means on average, these 20,000 stars on average are billions of years older than our sun. And this is one example I can think of where older might be better, because if you're older, you've had more time to cook up something that might be interesting. In any case, 15 to 50% of red dwarfs are thought to have habitable planets. There was an announcement of another red dwarf system yesterday with 3 planets. I think that they're a good place to look for ET, so we're going to be doing that. Let me sort of wind up here by saying, well, what would be the reaction? Because Mr. and Mrs. Front Porch, to the extent that I ever go to a cocktail party, will come up and say, once they learn what my job is, they'll say, so what happens if you find them? Would you even tell us? Right? Most people figure, no, the government would swoop down and shut you all down because they couldn't handle the news. What do you mean they couldn't handle the news? 1/3 of them believe the aliens are here, right? and they're not terribly discomfited by that thought. So I don't think that that's it. We have had a false alarm. Joe can tell you all about it. In 1997, for most of the day, we thought maybe we had found something, and nobody was interested, right? The mayor of Mountain View didn't even show up, right? The only thing that happened was at 9 in the morning when I was asleep at my desk, one of the science reporters from the New York Times called up. So that was the interest. So that's what will really happen. It will be a tremendously big story, but we won't have a message. We won't know what they're saying. That's an artifact of the technology used to search. That would require building a much, much bigger instrument, but I think at that point, money would not be an issue. So bottom line, if this idea of SETI, of looking for signals that might be being sent our way, if that idea is correct, if it has legs, then this experiment, it's not something for the ages. This is not something that'll work 3 centuries from now. If it's going to work at all, it's going to work in your lifetime. And I think that you should be prepared for that, because what that means is that, you know, for 200,000 years, the history of Homo sapiens, we have liked to think that we are perhaps astronomically or biologically or maybe intellectually special. And we will learn in an instant that none of that is true.
All right. So thank you for that perspective. Now, again, Seth was sharing his views on when we might find a signal, which is a particular kind of life and a more advanced kind of life. I did get an email from Donald Trump this morning assuring me that if we do find a signal, he will build a dome. So rest assured, we have nothing to fear. Donald is here. So with that,
among us, aren't they?
there's a good introduction for you, a good segue for you, Fergal. Maybe get it a little more
I
serious.
had no idea I was going to have to follow Seth Shostak up here. The energy's going to go down just a little bit. I work on the Kepler mission. I'm going to take an approach to this question of radio signals are all very well and good. It would be great if we contacted something, tried to contact us that want to communicate with us. But even among humans, there are far more people than there are people who are emitting radio waves, and there's far more different kinds of life on the Earth than are technologically capable. So a better approach to this, in my opinion, is to start by looking for life of any form at all. And the way I think we should do this, the way I'm going to focus on anyway, is I'm going to talk about life on planets around other stars, life which is outside the solar system. I'm somewhat biased on this. I work for the Kepler mission. It is our job to find planets around solar systems, so we're trying to drum up some business for it. The 2 big results from Kepler, if you haven't heard them, that I want to share with you is, number 1, is that in our galaxy, we now know that there are more planets than stars out there. Now, when I was growing up, when I was reading those astronomy books from the library, we didn't know about any planets out there. There were people who were arguing, very logically, that planets were very rare. We now know that they are extremely common. More has been work done by a colleague of mine, Chris Burke, who has established that if you just look at the sun-like stars, stars that are like our sun, and you look for planets which are about the same size as the Earth, about the same orbital period as the Earth, take the same amount of time to go around their star, somewhere between 2 and 25% of those sun-like stars has an Earth-like planet by that definition. Now, that's a pretty broad range, you think about it, between 2 and 25%. If you heard that there was a horse that was a 25% chance of winning a race, you might put a bet on it. If you woke up the next morning and discovered there's only a 2% chance, you might be pretty unhappy. But to go from a range of where we had no clue what the number was at all to get to within a factor of 10, as Seth said, a factor of 10 for an astronomer is basically the same number. We've done... And I tell my referees that all the time. So let me go back to that definition a little bit. I said planets which are about the same size as the Earth and about the same orbital period. That's something of an unusual definition of an Earth-like planet. You might talk about trees and waters and mountains and people and stuff. I use that definition because with the Kepler Space Telescope, those are the only two properties of the planet we can actually measure. So all those pretty pictures that you see of Kepler planets that show up in the media, that show up in your Facebook feed, they owe more to the imagination of artists than they do to any constraints we can place on the planets themselves. There are things other than the size of the planet and its orbital period which are important. Size is important. If the planet is too big, it's probably a gas giant like Neptune or Jupiter, and there's no rocky surface to walk on. If there's life there, it's not life like us. It's not life like we recognize, and we could observe those planets and not understand what we are seeing. The other important thing I talked about orbital period, if a planet is too close into its parent star, it's going to be too hot, and any water on the surface will boil off. If it's too far away, all that water will freeze into ice. It won't be available for life. One of the few things I know about biology, and I stopped taking biology when I was 14, but every biochemical process we know about takes place within water. We can't imagine any form of life that doesn't involve water. At least I haven't heard about it. Feel free to contradict me in a minute. So we talk about these things, maybe 2%, maybe 20, maybe 1 in 50, maybe 1 in 4 of the planets of the stars out there that are like the Sun, host a planet like the Earth. By that definition, there's also important things like atmosphere. What's in the atmosphere? Is it full of poisonous gases? Is it full of nitrogen, like our own atmosphere? Is there water there? Is there any evidence of the sort of gases that life produces that we could detect? And the way to answer this question, the way to move forward from Kepler, is to take what's called a spectrum of the light from a planet. As we're showing in the diagram up there, if you take the light from the Earth and you pass it through a prism, you can see that the light from the planet is brighter and fainter at different colors. That's all that a spectrum is. In the picture that I show up above, I'm showing a spectrum of the Earth starting from green wavelengths all the way out to red, and then pushing further on into light, which is too long of a wavelength for human eyes to see. This is what we call infrared light. This is the light that your remote control in your television uses to work. If you look at this spectrum, you can see a number of lines and bumps and wiggles and glitches in that spectrum. These are caused primarily by molecules in the Earth's atmosphere, which are very interesting to us from the point of view of establishing if there's life on that planet. You can see some of them I've marked off with H2O. That's water. Knowing if there's water on the surface of the planet would be very important for this question. And that big spike down there, just slightly to the right of the middle, that's oxygen. Now, oxygen is a very reactive chemical. If there's not something producing oxygen, that oxygen is going to react with stuff. It's going to disappear on timescales which are short from the point of view of an astronomer. The oxygen on the Earth is being created by life. And so if you take the spectrum of a planet and you see water and you see oxygen, that's very strong evidence that there is life on that planet. So I see this is the way forward into doing this. The problem with this, now, before I go on, I should say there's some astronomers who disagree with this. They say there's possibly other mechanisms for coming up with oxygen. This is not settled science, but I think it's the way forward. Certainly the best approach we have at the moment. The problem is that these planets are very small and faint. They're very far away, and they're very close to a big, bright star. In order to take a spectrum like this of a planet that is not the Earth, you will need to suppress the light from the star by a factor of about 10 billion. That's a lot. People are working on this. They haven't figured out how to do it yet. Looking at those technical challenges, I estimate it's going to take them maybe 20, 30 years to solve that problem, and then maybe another 10 years to get the mission designed, funded, built, and launched. So that's my prediction.
Okay, so I have a special respect for Fergal as an astronomer because think where he grew up. You know, so he grew up in Ireland. He had to take everything on faith that there were even stars. So imagine his surprise when he moved to California. He says, "My God, they were right. There are stars out there. All this studying hasn't been in vain." Okay, so what's your prediction in terms of when? Says the when?
So I asked my friends and other people who work in the Kepler mission, and I heard everywhere from never to 6 years' time.
Okay.
So I'm going to split the difference here. My guess is going to take about maybe 30, 40 years, maybe a little bit longer, to get all the technology developed, funded, built, and launched. So that's going to be my prediction.
Okay. Thank you. Natalie.
Yeah, now I will have to go with Fergal in terms of, how we need to look at life in the universe. We need to collapse the walls of just looking for something that looks like us or think like us, etc. Which means that opens new horizon, literally, and that opens new horizon both for the SETI aspect of it or what we call more of the astrobiology, the little guy, the microbe, what Seth doesn't think is an intelligent part of life, but actually, after 4 billion years, led to somebody like you, Seth. So, you do have to think about life as a continuum, and microbial life is going to tell you about intelligent life. But to go to the point of today's discussion about when, I guess that there are two aspects of it. There is the planetary exploration in the past 40 years that has been building on a program, a continuum that shows you, what the geological history of a planet is, what the past climate of a planet can be. Like you see Mars behind me. We have learned from Mars that we have a planet that looks a lot like the Earth. Just look like the Earth, it's not the Earth. But we know that conditions were habitable in the past on Mars. We know that climate was favorable and things change. So Mars is, for me, I don't know if it will be the first place where we find life, but this is the first place we have started to look at habitability, and we're going to start to look for life soon. Actually, there is a ExoMars mission on its way now that is going to start to look at spectrum, things that you would like to see, looking for methane, looking for oxygen, signs that life could have been on Mars in the past. And now we know now that we have methane that is seeping out of Mars. Methane can be created in a number of ways, but the interesting thing on Mars, for instance, is that this is a variable signal. And what that means is that it can be an event somewhere. Maybe it can be geological activity, but it can be also related to biological activity. So this hypothesis is very much possible. So definitely in my mind, Mars would be, possibly the first place where we are going to find something, because we have an integrated program that has been helping us understand what its ability was in the past. So Mars had lots of water. It had what Bill was discussing about energy, lots of volcanoes, nutrients in the minerals, but also shelter. And shelter is very important for life. So in the past you had an atmosphere. It's now gone, but that was the primary shelter for potential life on Mars. So that would be one place where I would be looking for having results sooner rather than later. And then there is obviously, Cassini, and we might talk more about that with Mark, and all the moons that we are discovering in the solar system. And all of a sudden we discover that there are oceans. We have heat that is generated by gravitational tides from these giant planets, and the shelter is there, and the nutrients is being provided to potential life in the subsurface of these moons and planets through the exchange with the surface. So all of a sudden, in the past 40 years, we came from just having a glimpse of little dots through telescope to having full-blown words that we can understand. And what we also understand is that you don't need to be a planet necessarily to be habitable. The notion of habitability has completely changed in the past 40 years. We came from understanding habitability as a distance from a parent star, and you were either inside it or you were outside it. And today this is not the case anymore. A number of worlds in our own solar system are outside the habitable zone. Yet they have a habitable environment, and very promising one. Oceans, maybe hydrothermal system inside the moons of Enceladus and Europa. So the solar system is really the place where I think, just because we have lots of missions going at them, we'll have sooner rather than later a response to, are we alone? But to Seth's point, we know that there is no intelligent life or technologically intelligent and advanced life in the solar system. But still we can learn a lot, and we can learn a lot about how to go and find ET, and find ET faster by understanding how life evolves with its environment. And this is one of the great lessons of astrobiology in the past few decades, is that we realized that Life doesn't just show up like that. But when you have transition from prebiotic chemistry to life, all of a sudden something very strange happens. Life transforms its environment. A planetary environment is going to give you the condition for the physical, chemical condition for life to happen. It will tell you what type of life is possible or not possible. But once life is here, it's going to modify its environment. And so to go back to Fergal's discussion and to Seth's discussion, we have to think in terms of looking for intelligent life and advanced life in terms of coevolution of life and environment, which means that every single planet that we are looking for is going to be a unique experiment. So looking for ET, you are going to look at something that is different. Every time you look at a planet, you are going to look at a different experiment. Is ET looking like us? Who cares, you know? There is probably a lot of intelligent life out there, but it's going to be very different. Are we searching the right way? I don't know. But what I'm saying is that probably the solar system is going to give us the answer first, but by learning what we are learning right now, we will be finding ET sooner, because the answer is also contained in the way we are looking at the solar system.
All right, thank you. Nat, this is what's fascinating about working at a place like the SETI Institute. You can tell perspectives tend to be colored a little bit by the kind of work that's being done. So here's Seth, who won't be happy really until he finds a signal from something that Donald will protect us from. And then we have Fergal, who really won't be happy until we're looking at life on exoplanets. Quite a challenging technical feat. And Nat is focused on microbiological life. Probably, I would agree, the first places we're likely to find the presence of life beyond Earth is right here in our own solar system, and yet of a very basic life form. And with that, Mark, we'd love to get your perspectives.
Okay. Well, I am a physicist and mathematician, so I'm going to take a kind of a mathematical approach to the problem, and I'm going to go for broke with Seth. I want there to be intelligent life in the universe. And so what I did is take this image of the tree of life. It came straight out of Wikipedia, so it has to be true. But I turned it into a kind of a board game, and the idea is that you are a fledgling young planet, and you are sitting there at the base of the tree of life. And the goal of this game is to get to the winner circle, which is an upper right, where there are big brains, intelligence, a creature that can actually look down on that tree of life and say, wow, look at that, that's really cool. There are a couple of checkpoints along the way, and the game is to basically roll the dice and see if we can get past each of those checkpoints. There's something very peculiar, though. I sort of gave away the ending. When Earth played this game, we got all the way to the winner circle, right? We are here. And what that means is that we have a very particular perspective where we can look down on that tree of life. We can look down on that game. We passed all 4 of those checkpoints. We could say, wow, life is easy. I bet life is plentiful on the universe because look at us. We came along. There is a mathematical flaw in that reasoning, and that is that we have what would be called a biased statistical sample. We are looking at ourselves. And you could just imagine sort of taking it to an extreme. Suppose every planet in the universe played this game, and only once did any other planet get into the winner circle and have that intelligent species. That intelligent species would look at its tree of life, and it would say, wow, this game was easy. I bet life is plentiful. But they would be wrong, and for us to make that same argument, it is flawed. We could be wrong about that. So let's just start at the base and play the game. The first question mark that you can see, that's biogenesis, the beginnings of life, some form of life. We know that that happened rather quickly on Earth, and so some people have argued if it happened quickly, it's probably rather likely. I would say that might be right, but on the other hand, we've got to remember that we are in a biased position. If life didn't occur quickly on Earth, then we wouldn't be here to look at it. And therefore, it's a slightly flawed argument to say life is easy just because it appeared quickly. It could be that it does appear and it is a very likely outcome. It could be it is a fantastically improbable outcome. We don't know. The next checkpoint, the next question mark, is a very interesting one, the origin of eukaryotes, which are these more complicated cells, not just the incredibly simple ones that we started with, but the eukaryotes have a nucleus. And the story, as we understand it, is that one day this big archaean was sitting around, and a bacterium came along and sort of found a hole through the membrane and entered into the archaean, and that bacterium took up residence there. It became a mitochondria, the nucleus formed, and that archaean became a eukaryote, the first eukaryote. And we are all descendants of that one event. It took about 2 billion years, so half of the history of the Earth was spent waiting to get from biogenesis to the first eukaryote. And, you know, most of the time when a parasite enters a critter, neither of them turns out to like it very much. So it could be that turn of events was, in fact, incredibly improbable. But complex cells are one of the requirements to get up to the winner circle. The next step, the next question mark there, is basically where sexual reproduction appeared. That means you have 2 parents instead of 1. That means every individual is a unique genome. And once you get to sexual reproduction, evolution explodes. And that's why the yellow piece of that tree has so much variety on it. It has slime molds and it has us and everything in between. And, but that's because of sexual reproduction. It did not have to happen. There are mathematical reasons why asexual reproduction seems to be preferred in a lot of numerical experiments that have been done. So it may be that sex was inevitable, but it may also be that it was fantastically improbable. Finally, you get to life. Now, we could imagine a planet where all evolution ended with elephants and lions and bears, and nobody building radio telescopes. What is it that made that transition so that genus Homo became as intelligent as we are? That's a really tough question, because the thing is, big brains are not the natural end state of evolution. Big brains are big drains on nutrition, on metabolism. There's got to be a good reason for the brain to get that big, and we don't really know why that happened. It could be that intelligence could have been a fairly likely outcome, but on the other hand, intelligence does not seem to be foreordained. It could be fantastically improbable. So you put that all together, and my bottom line is that I don't know when we're going to get to any of these points, how often they occur, but mathematically what I worry about are the biases when we ask these questions. My colleagues are very optimistic, and I hope they are right, but that's my bias. Consider that we see life everywhere on Earth, everywhere we look. It is built into our brains. So not only are we biased by living on a statistically unusual sample, Earth, we are biased because we see life everywhere. And if we see life everywhere on Earth, then we're a lot more inclined to see life off the Earth. And we're a lot more inclined to want to see life off the Earth. So that's a bias that we have to look at very, very closely. So my concern is that if we play this game, even if 1 or 2 of those steps in the process, one of those gates that we had to cross, turns out to be fantastically improbable, then there is a lot less life in this universe than we want there to be. And looking at the solar system and looking for ET might just take a long time, not because our technology isn't capable, not because we're going to interesting places, but because it's just not there yet, or not there currently. So if I had to predict, I would say there's a 50-50 chance that my colleagues are right, and that we'll see life in the next century, and there's a 50-50 chance that we'll see life never. And the reason we have to study this problem is because we could be alone in the universe, and the stakes are so high that we really have to answer that question.
And that's what the SETI Institute is all about, in a nutshell. So actually very interesting, as now you know we're all related, so we're all family here. We all are descendant from the eukaryotes, and we have cousins who are slime mold. So this is a good example of why, you know, the family photo album isn't always that attractive. But, so I'd like to start off with a question to the panel. It seems clear to me that finding life of any type at its most basic level would be a transformative moment in human history. Do you believe it would be equally transformative if we were to find evidence of past life, not necessarily current living life, for example, on Mars? That if we could find the clear, solid evidence that life had been there, but it is not there now?
I don't know why you're looking at me like that. This is a very important point, Bill. I guess that Mars is definitely the closest planet to ours. Very different, but similar enough that we can think that life, you know, as we know it, could have evolved on it. And there are a number of possibilities on Mars in terms of past life. The first one is that life evolved on Mars, and it was all different. The environment was similar, but it evolved something. And so it is there. It means that there is a second genesis on the second planet of a system of 8. And that starts telling you a little bit more about your game, Mark, about the statistics of life, at least in our solar system. Can we expand further? That's another question, but at least that gives us something to start on. The second one is that, of course, nothing happened on Mars, and this is another, another conclusion. Can we expand that to the universe? I don't know. Finding microbial life on Mars that relates to us, to me, is probably as close as exciting as finding a second genesis. And here's the reason why. Mars and the Earth have exchanged a lot of material when they were forming, just because of orbital mechanics. It's easy for rocks from Mars to go to the Earth, and it's somewhat less easy, but feasible for pieces of Earth to go to Mars. And so as they were forming, the two planets exchanged a lot of material. So let's imagine that they were seeded by exactly the same material. And that, life started on Mars and life started on Earth. Maybe we are Martian, maybe they are Earthlings. We don't know, but we are cousins. And this becomes really important for us because we don't know what life is, and we don't know how it started on Earth. And we will never know. We will never know for the same reason as we're here today. Our planet is a very dynamic planet, and tectonics and geology have erased the record of all the ancient rocks that were at the beginning of the history of the Earth. And so the oldest one we've found so far are 4.1 billion years old, and already we have potential traces that life was there. As Mark said, life started very early on. But the time when prebiotic chemistry transitioned to life, this record is gone from our planet. And if we're sharing some seeding material with Mars, Mars doesn't have plate tectonics. The geological activity was much less, which means that somewhere in an outcrop sitting on Mars, you might have the record of how prebiotic chemistry came to be life, and that would help us understand how we came to be. So this would be profound in a number of levels.
You asked for the reaction. It doesn't matter whether you hear this, actually. You asked for the reaction, Bill, but I think that experiment has been run. For those of you who can remember the biggest science news story of 1996, and that's all of you, right? That was the claim that they had found fossilized Martian microbes in a rock that was picked up in Antarctica. And what was the reaction to that? 4 days straight, big headlines in the New York Times in font that hasn't been used since, that you could read from low-flying aircraft, right? The public was extraordinarily interested, and this was life that had presumably been dead for 4 billion years. So I think that the reaction would be substantial.
And knowledge would be profound for us, because once again, the record is gone here.
Yeah,
absolutely.
It's like being an orphan and looking at photo pictures and finding a net or some relative somewhere and, learning who you are that way.
When we talk about candidates for life, not only do we have, of course, Mars, and particularly those regions just below the poles of Mars where there still appears to be liquid water evident. Other candidates that come to mind are Europa, which is getting a lot of attention. There are NASA missions planned to explore Europa, but also Enceladus, the moon of Saturn. Would anybody in the panel care to comment on what they believe might be found when we get a closer look at those moons?
Well, I can speak to Enceladus in particular. I know that at least there are very, very preliminary plans to actually send a mission out to Enceladus. Enceladus, by the way, a small, about 300-kilometer moon of Saturn, which has geysers. It has essentially cracks in its southern hemisphere where sprays of salty water, or salty ice, in fact, are coming out, and they've been detected directly by the Cassini spacecraft, which has been orbiting Saturn since 2004. There are very preliminary technological thoughts about how to actually take a spacecraft, send it to Enceladus, and then drop a probe, essentially a submersible probe, into the interior ocean of Enceladus through one of those cracks, which are not very deep, as we learn. And it would be the easiest and shortest way to actually take a look inside one of these oceans. Inside many of the satellites and planets in the distant dwarf planets have an interior salty ocean that could be the right kind of place for life to form. So imagine maybe in a few decades beyond other people's horizons, we're actually looking at the undersea environment in Enceladus and seeing little critters swimming around. And that would be one of those great moments of proof that there's actually frequent biogenesis in the universe.
Alan Stern was asked before New Horizons got to Pluto, what is he going to find there? And he said, we will find something wonderful. And I think if we send a probe to Europa or Enceladus and we get under that ice crust, whatever we find will be wonderful. If we find life, that answers this question. If we don't find life, we've got the conditions that are perfect for life, and we can start wondering, why didn't it form? And that'll give us, start to give us some sort of insight into how common it is that biogenesis happens in other places around the galaxy. So I think that would be one of the really cool things for NASA to do.
Fergal, I will go with what you are saying by adding that we need to look at our solar system as a natural lab to understand who we are, where are we coming from, but also what life could be outside the solar system. Although I think that there might be more biochemistry than what's feasible in our solar system. But definitely we need to use what we have. This is our Rosetta Stone. This is where we are. This is who we are. And so we need to use it to understand what's beyond us.
Saturn is a lot closer than the nearest star.
That's right.
That's the good news. So we've had some interesting perspectives here. I hope you've enjoyed this. We want to get maybe some discussion going. Before we do that, it's worth observing that, as you would expect, it's very difficult to pin down a scientist in the absence of data. Very data-driven. And so, we've had kind of wide-ranging guesses. You notice that there's nobody who's actually gone on record and say, here's when. So, in the parlance of the game show host, I would say, thank you for playing. I'll go ahead and share a perspective that I think that within 30 years from now, we will find evidence of life within our own solar system. I'm not sure whether that's on Mars. The polar regions are going to be explored, we hope, by a mission yet to be funded, but in the works, called Icebreaker, which is a probe that they hope to launch and land on Mars, launch in 2024. There are missions planned for Europa. Not sure if there's missions at this point planned for Enceladus. But
they're in the works.
They're in the works, yeah.
So I'm of the opinion that within 30 years, we're going to find evidence that, to the point made earlier by the panel, that life formed early on Earth. It seems that the ingredients were there early on for at least basic life to evolve. I think Mark raises some interesting points about the ultimate evolution of life into the species who can ask this question. But basic life, I'd like to believe, is more prevalent than we can imagine. So another thing before we open it up to questions, not only is this a competitive sport, but we're involved in a competitive sport in terms of our fundraising efforts today. So I noticed that we've dropped to 4th place on the leaderboard here, which is a result of the fact that you guys are all in here and just enthralled by what you're hearing and nobody's out there. So we hope that to be changing. What's particularly depressing is that the #1 is the Multidisciplinary Association for Psychedelic Studies.
They should come here. Come on.
I don't know what that says about Silicon Valley, but maybe it sums it all up in one nice thing. So anyway, please remember us on Silicon Valley Gives Day and see if we can move up the leaderboard. What I'd like to do now is open up the floor to questions. We have a microphone up in the front. If you have questions for our panelists, please make your way to the microphone if you can. If that's too difficult, we can probably get a microphone. Maybe Lee, could we arrange to get a microphone for people who seem to be trapped in the middle? First,
from David Morrison. For searching for life in the solar system, whether Mars or elsewhere, I have not seen any evidence that anyone has figured out how to build a life detection instrument. What would it be? What would it do? If we can't bring the stuff back, what could you analyze that would tell you whether something either was alive or had once been alive?
That's a very good point, and that goes back to the question, David, that we don't know what life is. We know when we see it. And we are searching for something we don't know. And basically what we are trying to do right now is to go to places, and one way of doing this is going to places we believe are good analog to those planetary environments that we want to visit. And we are developing instruments that are trying to figure out, what would be left in an environment that is high radiation, what would be left in the ice, etc. So right now we're putting instruments together. Unless you have a rabbit that is going to jump in front of your rover on Mars, or something that is going to fly in front of your camera as you are crossing the geysers of Enceladus, it is going to be down to biochemistry. And so it is extremely difficult to get a instrument package that is small enough that is going to give you the information you need. But this is what we need to do now. And that also tells us that we need to bring back those samples. We need to have the capability. We need to have the resources to bring the stuff back on Earth, because it's always going to be better than what we can put on a spacecraft. So right now you have all sorts of instruments. You have Raman spectrometer looking for organics. You have something else looking for pigments that go with the Raman. You have biosignatures that are morphological, that are chemical, that are physical, that, name it. But you cannot have any one thing taken alone that is going to tell you this is alive.
Okay, I have a question for Seth, I think, or other panel members may contribute too. But I'm working with some of the ATA data, and my bias has been that when we find the signal, it won't take very long to figure out what it means. But I'm reading a science fiction story by Gregory Benford, where somewhat in the future, the Earth and the Moon are awash with ET signals, and nobody's figured out any of them. So my question for you is, when will the signal be decoded once it's been detected?
All right, Jeff asks, when will we decode the signal? I appreciate your optimism, Jeff, in assuming that we will find the signal. For those of you who are technically inclined, and I suppose that's a large fraction of you, the reason that you don't get the message right away, you don't get the bits, is because, of course, we average the incoming cosmic static over seconds or minutes or whatever the integration period is in order to find weaker stuff. It's like making a time exposure at night with your camera. You lose all the temporal information. So the bits, which are presumably coming in at billions, or millions at least, millions of times a second, like a TV signal, they all go away. But if you announce tomorrow, hey, we picked up a signal coming from 847 light years away from that star system over there, I think money will no longer be a problem, okay? And this should worry our fundraiser perhaps, but money will no longer be a problem, because you will get the money to build a very much bigger instrument that can have the sensitivity to find those bits. Now, how long after that do you finally figure out what they mean? Because they're not going to send an empty signal into space unless it's a very short signal saying, we're here, let us know you're there. Otherwise, they're going to send info. They're very far away. They're not going to wait for you to get back to them. They're going to send everything. They're going to send a lot of stuff. And I think that what you would do at that point is you would take all these bits and you would put them on the internet. And it would be like decoding the hieroglyphics. That was done very quickly because there was a lot of material. And if there presumably be a lot of material and you have the whole world working on it, and could they ever figure it out? I don't know. Personally, I'm somewhat skeptical that they'll ever figure it out or will ever figure it out, because to me it's like giving Neanderthals, right, a digital television signal. Neanderthals were not that stupid, but they would never figure it out. But that's okay. Even if you don't figure it out, at least you know you have company.
Well, maybe you'd finally be able to beat the Multidisciplinary Association for Psychedelic Studies and funding.
Maybe they will decode it for us.
Hope springs eternal.
So my question is at the other end of the spectrum, which is back to exchanging rocks with possible evidence of the transition to biochemistry. Is it possible to look on the moon? Because that's even closer than Mars. I mean, presumably we exchange, doesn't have the gravity, but we exchange rocks with the moon.
Yeah.
Would it be likely that if we looked on, say, the near surface of the moon, we might find some?
Yeah, exchange of material, actually, it is much easier to get material from Mars to the Earth than it is to get material from the moon to the Earth, because anything that is on the moon, on Mars, is basically orbiting the sun, and it just goes off in some pathway. It gets banged off Mars, and then the Earth gets in the way and it lands. If something comes off the moon, it's still orbiting the Earth, and you have to get rid of all that spiraling energy until you get it down to the Earth. So when we find extraterrestrial meteorites that come from the solar system, they are much more often from Mars than they are from the moon. But that being said, we actually have pieces of the moon already. We can go there and get them, or we can wait for them to fall. They do fall occasionally. I'm sure they have been analyzed in the same way that that chunk of Mars was analyzed that apparently was thought to contain fossils but did not, and that was certainly a worthwhile avenue.
Yeah, but what about Earth rocks maybe landing on the moon?
Well, it's actually, this is a dynamics problem, so this is where I know this stuff. Getting stuff off the Earth is much harder than either the Mars or the moon because we've got a bigger gravity. So it's much more likely, for example, for life to form on Mars and then accidentally seed the Earth than for life to form on Earth and then accidentally seed Mars, because getting material off of Earth is much more difficult.
Thank you.
Yeah.
I will add something that goes back to David's question as well, is that the reason why we would prefer to search on Mars is because Mars is going to give you context. And it is really difficult to understand what's alive and what's not, or what was alive and is not anymore. You need context for that. And finding a rock that has been dumped by an impact and an ejecta somewhere randomly at the surface of a planet is not going to help with trying to reconstruct the conditions and the environment this rock and this record was formed in.
Right.
Okay, so sacrilegious question, and it actually turns out it follows the previous questioner. Have we ever considered seeding one of these planets with some life form to verify that we are right and it can in fact support life?
Marge!
Marge, is that allowed?
Can somebody get the mic to
Yeah,
Marge?
get the mic
I
to
think
Marge.
she has the answer to this question.
My name is Margaret Race, and I work on planetary protection, which is the biology of...
This is
and
the
science
planetary
policy.
police.
My boss is the planetary police. But anyway, so United Nations Outer Space Treaty is something that we've all been using to set policy for how we go into space. And there's Article 9 of the treaty says no harmful cross-contamination. And harmful is in terms of what you're doing to the science that you're going to do as well. So if you would seed something on purpose that could then perhaps spread there, that's not a good thing. So we are very careful in what we do to spacecraft before they go to a place like Mars. And so while it has been proposed that you do experiments inside a dome or something like that, right now you wouldn't do that. Although when they're talking about sending humans to Mars, that issue is coming up. What do we do about humans who go along with all of their microbes? So stay tuned.
Yeah, there's a shortcut to that. You can do lab experiment in Mars chambers, for
Yes,
instance,
and the
on
other
Earth.
thing, if we find life up there, I don't know what that says. Does that mean that Mars belongs to Martians? And what do we, and if Mars is different than that chart of life as we know it, does that make it a second Genesis? So then you go into ethical questions and theological questions. So it's science, technology, and lots of other things that come up.
Thanks very much, Marge. So you can rest assured that not only do we have scientists working on these questions, but we also have the planetary police making sure that we do so carefully. Terry.
Okay, Terry Turman, yeah. I have a question for Fred Mullally. You said it would take about 40 years to be able to block the light of a central star by a factor of 10 billion to see its planets. I've seen a proposal that looks like for a star blocker that would be about 50 miles from the telescope and block the light. It looks like a big circle with a lot of pointy, it's like a sunflower with a lot of pointy petals around a big circle. And this is the design, and I presume that's well thought out. And isn't this really a budget issue rather than a design issue to see planets around stars?
Yeah, so the idea you're talking about is an occulter, and it is basically, the idea is very simple, is you have a big telescope out in space, and then you put a big shade further out in space blocking the light of the star. And because of the unusual properties of light when you treat it as a wave, if you shape that sunshade just the right shape, light from this very central star will get blocked, but light from a very small ring around it will still survive. So the history of this, just to go back a bit, originally people said, we're going to use the properties of light and build something called an interferometer. So we've got multiple telescopes in space, and we'll combine the light just right so we block out the light from the star. It's going to be easy. So NASA said, all right, here's a bunch of money. Go do that. And they came back a few years later and said, well, that's a bit harder than what we thought, but look, we've got this great idea. We built something called a coronagraph. We put this little thing to block the light deep inside the spacecraft. And I said, all right, here's some money. Go figure out how that works. And they came back and said, well, it turns out that's a little bit harder than we thought as well. But we could build an occulter. And at that stage, sort of the enthusiasm for NASA for funding the money to establish the feasibility of that had sort of died off a little bit. And so this does seem to be our best approach at the moment toward solving this problem. But to say that it's technologically solved yet is a bit premature. People still have to work and still have to make sure that it does work. Because it'll be a lot of money to do. Yeah.
but it's more than...
It's...
Use its hand on mic. But Terry, it's more than just budget, because it isn't 50 miles. The distance between the telescope and the occulter is thousands of miles. If somebody have a better number. It's a very, very big distance, and that means now you have to coordinate these two things when you want to point this instrument. So that's a problem too.
Yeah. So if you do build one of these, you'll spend most of your time not finding planets with this spacecraft, because you're waiting to get that occulter into just the right place. Some people see that as an advantage. One cosmologist says, and then while you're moving the occulter into place, you can do some real science. That's when I lost all interest in this project.
So before we jump to the next question, I know it's a little after 1. We may lose some of our friends from Microsoft. I do want to thank any of you who have to leave at this point very much for attending and joining us. I do hope that those of you at Microsoft will remember that if you are interested in supporting the work of the SETI Institute, your donation today goes a lot further because your employer is going to match, and we're so grateful for Microsoft's support and for your attendance. So thank you for that. We have been, as well, by courtesy of Microsoft, been granted a little extra time here. So we're going to go about another 5-6 minutes of Q&A till about 1:15, and with that, you have the microphone.
Yeah, so my question was, earlier you were talking about looking at red dwarf stars. Maybe my question is more inspired by science fiction than science, but I read that the planets are usually tidally locked, and one side is always day and the other side is always the night. So how do you have life in such a place?
Intelligent
It's the morality police of science.
It's hard to keep set down, but we're learning how.
Yeah, the question is a good one, and that is, if you have a planet around a red dwarf star, that red dwarf star is really pretty dim. The planet has to be very close in order to be habitable, in order to be able to have liquid oceans. But if it's that close in, it's going to get tidally locked, just like the moon. One side of that planet's always facing the star. The other side is always facing away from the star. So the far side will be very cold. The atmosphere will freeze out in useless heaps of snow and ice on the ground, and that's it. It's dead, Jim. Well, that was the view 15 years ago, but since then people have done studies, and these people can probably talk about that, in which they show, look, if you really have a planet like that, the winds will carry some of the heat from the hot side to the back side. If you have oceans, the ocean currents will carry some of the heat from the hot side to the back. So the atmosphere won't freeze out, and sure, it's too hot on the near side and too cold on the far side, but in between, it's like Northern California.
We're going to be could be a very narrow habitable zone just around the night side,
Right, yeah,
just at dusk.
Housing will be dear.
Yeah.
Like California.
A planet, a rocky planet in the habitable zone of an M star is a very different environment from the Earth. The stars are much more active. They're spewing out these flares, there's explosions on the surface, there's a high energy radiation. It will be a very different environment from the Earth. But that goes back to what Mark was saying. Just because it's a different environment, it might be life which is different to us in many ways, but there could still be life there. So to me, it's a big open question. What we would find if we actually got to land a probe on a habitable zone planet around an M star.
You can make the argument if you have a habitable stripe on a habitable zone planet, you're actually much more interested in finding more room. So you may just be saying, is anybody out there with more space than we have here? Question.
I would like to ask, to what extent are you using the origin of life on Earth to inform your search for life elsewhere? In particular, I'm referring to some recent progress they've made with white smokers under the ocean. There's one group that seems to think that they have managed to duplicate the Krebs cycle, you know, the energy production within a cell, using just white smokers. Thank you.
Yeah, well, once again, I'm not a biologist, but where I can respond to your question is that definitely what we are learning from Earth, it really helps us design and conceive the type of search we want to do on other planets. And when you have an environment like Mars that tells you, you know, there was water, then there was this, and there was that, there was energy, we had volcanoes, we have hydrothermal springs, we are finding the evidence of that, then you can go back to the type of life you know on Earth. But it's never a problem to find environments that you can relate to. I think that what is harder for us is to conceive something we don't know. But in fact, what's going to happen is that 99% of the universe and probably the solar system is something we don't know. And so that, you know, goes back to the whole discussion here. Yes, let's use our solar system as a natural lab, as a way to conceive ways to search for life as we know it, understanding that life as we know it is only probably a very small fraction of what's out there.
Mike Fisher. What do we know about the origins of the tardigrade?
The tree of life, prebiotic chemistry to life. The origin of the tardigrade, what I know about the tardigrade, and once again, I am not a biologist, but what I know about them is that you can fry them, you can freeze them, you can expose them to the vacuum of space, and it seems that they are absolutely immortal. They are indestructible. So there is definitely something we need to look into their biology and how they can adapt and survive, because we might have a number of clues here, not only on how could we ourselves survive, you know, these conditions, or even as they go dormant for a long time, possibly travel into space, or survive in different planetary environment. So I don't know about the origin of the tardigrade. I know that, you know, well, I've learned somewhere that people say that they are aliens, actually, because we don't understand them. So to me, that's the easy answer. We don't understand they are alien, you know, like we don't understand the Pyramid of Giza, so they were built by aliens. Yeah, we haven't met yet, but they are responsible for a number of things already. But tardigrades are an extreme version of adaptability on our planet, and they are telling us something about, you know, how we came to be, but also how we could spread and survive extreme condition in space and out there.
I'd like to invite you to comment on what seems to me to be the tragedy of SETI. That is, the universe, or at least the galaxy, is so large that the likelihood that somebody is out there who will be detectable in the signal is pretty good. But if and when that's detected, we shall have to realize that we have no hope whatever of interacting with it.
If I can interact with you. Well, I'm not quite as pessimistic, right? Within 1,000 light years, there are millions of star systems, so there might be somebody within 1,000 light years. And if they, you know, they'll know that our planet has life thanks to the kind of experiments that have been discussed here. They can see the oxygen in our atmosphere and stuff like that. And they may say, you know, it's worth occasionally sending them a transmission with some information. Because they're far away, hundreds, maybe 1,000 light years away, I think they would send a lot of information, because you're not going to get into an easy conversation with anybody that far away. Is that interaction? I mean, I studied Latin in high school. It took 2,000 years for Cicero's words to get to me, but it's still interesting. And I can, you know, where I can't talk back to Cicero. I can, but my psychiatrist says I shouldn't. But I consider that interaction. You're not going to meet them. Yes, I agree with that. But you might learn something.
I have, by the way, when the doors closed in Seth's office, I've heard Latin being uttered, so I think he's trying. I have not told his psychiatrist, however. All right, well, with that, I think we've come up to the end of our time. I'd like to thank our panelists and have you join me in thanking them for this lively discussion.